Welcome back, students. Welcome to the course Natural Language Processing. Myself Priyanka Gupta. I am working as assistant professor in Department of Computer Science and Engineering, Data Science Department at Institute of Aeronautical Engineering, Hyderabad. Today I am going to discuss about finite state automata and regular languages. Let's discuss about that. So topics I will going to cover about what is actually regular state automata is, what is relation between the finite automata, regular grammar, what is regular grammar, and what is regular expression actually. What are the difference between these three? What is relationship? What are the different types of finite state automata? So there are two types of finite automata that are deterministic and not deterministic. And then I will discuss about the other aspects of that, basic aspects of that. Let's discuss. So what is finite state automata? Whenever we will call the regular expression, that is, whenever we will call that is more than just a convenient meta language will be used. That will be used actually for the text searching. Whenever we need to do the pattern searching or text searching, we will use the regular expression. First of all, the regular expression in one way that is going to describe a finite state automata, that is one state to just represent the regular expression. That will be represented in the form of syntax as well as in the form of graph. Then any type of finite state automata, regular expression can be implemented as a finite state automata. Symmetrically, if I'll say any finite state automata can be described by using regular expressions. So in the second case, if I'll discuss what is regular state automata is, so the regular expression is one way of categorizing at one place the particular kind of formal languages that is called as a regular language. By using the regular language, we can just represent regular expression as well as the finite state automata. So both is going to be described the regular language. So that is how the finite state automata is. Now, what is relationship between these three? That is finite state automata, regular grammar, and regular expression. Following point can be considered to give as a clear view about this relationship between these three. So, as we know about the finite state automata, that are the theoretical foundation actually for the computational work that is going to give the pattern matching for the different cases, and the regular expression is one of the way to just describe them and represent them. Other case, we can say that any regular expression can be implemented by using the finite state automata, and any finite state automata in that case going to be just described with a regular expression. So that is how these are all different with each other. Next state, if on the other case I will say regular expression is a way to characterize a kind of language that is regular language. Hence, if we can say that regular language can be described with the help of both of the FSA and regular expression. So that are how three are interrelated. Regular grammar is nothing but a formal grammar that can be just right regular or left regular. So in another way to characterize the regular language. So that is how the grammar will be written for these cases. Now let's see how we will represent those in the form of diagram. So these three will be sourced with the help of finite state, regular expression, and regular grammar at one place. That is going to be equivalent whenever it is going to describe the regular language. So that is going to make the triangle actually. So here the regular expression is, here the regular language is, here the finite automata is. So that is a relationship between these three that has been suggested by Martin Kay. But whenever that is going to make the relationship between each other, that will depend on each other, and that is going to make a triangle shape of relationship. There are two types of finite state automata is. So first is deterministic finite automata, second is non-deterministic. So let's discuss about finite state automata. So it may be defined as a type of finite state automata, whereas every input symbol that is going to be defined and determine the state, and which is going to just give to the machine to just move to the further state. So it has the actually finite number of state in between whenever from input state to final state. So that is called as a deterministic finite automata. Why? Because there will be the finite number of state in between. So that is a description of definition of deterministic finite automata. If I going to represent with a mathematical way, that I can say the deterministic finite automata can be represented by 5 tuples. The 5 tuples are capital Q, summation sign, delta, Q0 state, and capital F. So these will be called as a, I will show you the discussion of that. That capital Q is called as a finite set of state. The summation symbol is a finite set of symbols that is called as actually alphabet of the automata. That is alphabet of automata. The delta is the transition function will be used for that. In that case, it will be just depend on the capital Q into the summation symbol. So that belongs to actually Q, capital Q. So that is a finite set of state. Next is Q0, that is a state, that is an initial state from where that the machine is going to be start, that is going to give one input from that will be processed from the Q0, that is the set of capital Q. Now F is a set of final state states. There can be a state states that is going to be followed. Q that is a Q of that will be F of subset of Q, capital Q. So this is how the mathematical way we can represent the deterministic finite automata. Whereas in the graphical form, the DFA can be represented by the different symbols. Whereas the state will be represented by vertices. Whenever vertices will be there, we will call that is state. That is one state has been just occurred. Whenever I am going to discuss about transition is there. So wherever labeled arcs are there, that is going to show us a one transition. Likewise, that the initial state will be going to followed with the empty incoming arc. So whenever incoming arc will be just going to come, that is called as a input state. Final state will be represented by double circles. So in upcoming graph, I will show you these all cases. So that is first we have to make a transition table. So that is how, suppose example I will take. If I will having a Q state, in that 3 states are there, small a, b, c, these are 3 sets. In summation, I am having the 2 states, 0 and 1. And initial state, I am starting with the small a, that is Q0 is equal to small a. And F is, that is a final state, I am going to complete with small c. So then the transition function delta is going to give the following, that is going to make a table. In that, current state will be there, next state will be there for input. Whenever 0 input is there, whenever 1 input is there. So whenever I will start with capital A, that is a current state, that is going to give the next state small a, right? Whenever 0 is there, small a will occur. I will start with A only, and that is going to give the next state, that is capital B. So whenever it is 1, whenever input is 1, then that is going to give the capital B. Then in the next state, if it's starting with capital B, the current state, then it is going to give the next state small b. Right after that, and then it is going to just transition in the form of input A, that is for capital A, right? That is going to just make a we can say triangle. Now again the current state, if it is C, capital C, then it is going to give the small c, and in that case whenever 0 is there, that is going to give the final state, that is capital C. That is how the graph is going to be made out of that for the deterministic finite state. Now the description of the representation of this particular example can be like this. So whenever the upcoming arc is coming, so that is the initial state, right? And that is again going to the next state, that is again going to the next state. Whenever 0 is there and whenever 1 is there, whenever 1 is there, that is going to go into the final state. So likewise that the DFA will be followed. Now, non-deterministic finite state automata, it may be defined as a type of finite automata, whereas for every input symbol, whenever it is occurring, we cannot determine the state to which the machine is going to be moved. Whenever the machine is going to be just transit in the next state. So machine can move to the any combination of state actually. So it is having the infinite number of state. So that is why it is called as a non-deterministic finite automata, NDFA. If I go to represent by the mathematical way, the same as it is, we have to follow with the 5 tuples that will be used for a deterministic finite automata. Only in the one case it will be different. So Q is the finite set of state, summation is the finite state of symbol, that is the alphabet for the automata. Next is delta, that is a transition function, whereas that is going to give the capital Q into summation, and that going to be belongs to 2Q, the two states of Q. Now the Q0, that is the initial state, that is starting from the any input, that is suppose Q0 one input is, that is going to process with the Q0, that is a set of Q, capital Q. And then it is F, that is a final state, that is going to give the F will be subset of capital Q. So that is a set of all sets. So that is how non-deterministic finite automata will be represented by different mathematical symbols. And whenever I'll go to the graphical representation of that, that is going to give the same type of, we can say, digraphs. So first digraph is the state. The state is going to be followed with vertices. Transition is going to be just followed with labeled arcs. The initial state is going to be followed with empty incoming arcs. And the final state is going to be give the double circle, as same as it is as the deterministic finite automata were. Now let's take an example for that, and we will discuss about that. So same example I'll take for that, and whatever change will be there, the slight change will be there. So Q is having the total three, we can say, inputs are there, ABC, small ABC. The summation is having two states, 0 and 1. Q0, the starting point is A, and the final state is C. So for that, transition function table will be like that. The current state, whenever A, capital A is there, in the next input, whenever 0 is there, then that is going to give the A comma B, two states, A comma B, small a. Then for the B, capital B, it is going to give the input whenever we are going to follow the one input. For the B, capital B, it is going to give the next state, capital C. And for the next capital, for the next input, whenever 1 is there, that is going to give small a comma C. Likewise, that if our current state is capital C, then it is going to give the next state for 0 case, B comma C, small b comma C, and that is going to give the next state for one input, that is C, capital C. That is how it is going to make a, we can say, triangle. Now let us discuss about the graph of that. So this is a graph, how it is going to be represented for the non-deterministic finite automata. So we will discuss in the next state out of that. Now automata as a directed graph. Whenever we use the directed graph for that, so what are the changes will be there? So we represent the automata as a directed graph whenever we are having the finite set of vertices, that is also called as a nodes, together with a set of directed link. So whenever directed link will be there, to having the set of vertices in that, connecting that with the we can say arcs. So that is called a pair of vertices, that is called an arc. Now we are going to represent this vertices with circle, arcs with that arrow. So whenever we are representing the vertices, that will be just shown with the help of circle. Whenever we are using arc, that is going to be follow the arrow. The automata is having the 5 states, Q0 to Q5. So which are going to be represent the different nodes in the graph, different states of the graph. So the first state, that is called as a state 0, that will be start from the start state, which is going to represent by the incoming arrow. So that is how it will be represented. Next state 4 is there, that is a final state, that is a accepting state. Whenever it is going to be complete, that is going to just completed by the double circle. In between, it is having the 4 other type of transition that will be represented by the arcs in the graph, right? So just connect that. This is how the 4 states 0, 1, 0 to 4 will be followed in directed graph. Now let's talk about one example, that is a SIP talk example, whenever we need to recognize with the help of finite state automata. So that is one example is there. These some sounds will be occurred whenever we just SIPs are just barking. So the regular expression for this kind of SIP will be actually will be followed with the /BAA plus, that is an link closure and an exclamation sign, and that is going to be just completed with the slash. So that is how this regular expression will be written for this bar example, SIP talk example. And for this, we are going to make a finite state automata graph like this. That is going to call as a that is a machine, that is a finite state automata, and that is going to give the set of string out of that. So here the first state Q1 has been occurred, that is going to be followed with Q1, that is going to be followed with Q2, Q3 and Q4, that is a final state. And if that is B is occurring, that is going to depend on the second, that is going to be depend on third, that is going to be depend on again if A is again and again occurring here, suppose B A, so again and again in the next examples it is going to occur, so that will going to be just followed with this upcoming arc, and that is going to be just completed with this exclamation. So likewise this we have to make the finite state automata graph for this SIP-TOC example. Now if I make a state transition table out of that, so how we have to do that? So we have to take the different states and inputs from this example, and then we have to just make a table out of that. So different states are 4 states are there, suppose 5 states are there, 0 to 4, so that will be 5. So 0, 1, 2, 3, 4, we have to make one table. In that one state will be there, input will be there, input are nothing but the B, A and exclamation sign. How many times it is going to just complete, just connect with this other state. So that is going to be just represented by this 1, 0, 0. If it is going to be just occur, 1. If it is not there, 0. It is not there, 0. Again, if B is not occurring, 0. A is occurring 2 times, 2, 0. Likewise that we have to complete this transition table for this finite state automata graph. So let's see the different parameter of finite state automata that will be just used in the algorithm of this finite state automata. Same things what we have seen in the earlier slides, but slight different can be there. So Q, the capital Q will be used for the finite set of n states, that will be used from Q1 to Qn. Summation is a finite input alphabet of symbols. Q0 is the start state, initial state, and capital F, it is a set of final states that and the transition function that is going to give the delta of small q and comma I. That is going to give the transition function, a transition matrix between the different states, whatever has been occurred in between this all states. So given a state that is q is set of capital Q and going to give the input symbol, returning a new state actually q naught, small q naught. So that is going to give us from the capital Q. And here the delta function that is going to have the relation between them, that is capital Q, is going to be just summation by this function, and that is till the whenever the finite set of n state will be followed. So that are all the parameters of finite state automata. Now regular language and FSA. So whenever it is occurred, it is going to make some classes. So class of language that is going to be defined by regular expressions, that is going to give the same equality, that is going to give the class of languages that are categorized by finite state automata. Because of this transition, we call this language as a regular language. Now, to give a formal definition for this class of regular languages, we need to define two concepts. Two concepts are nothing but whenever we will use the alphabet summation, that is going to give the set of all symbols in the language. And whenever we are using the epsilon, that is going to describe with the empty string, that is not included in this summation. So these are two formal concept of this regular language whenever we are writing this. And in addition, whenever we are using an empty set, that will be followed by phi. So this is how it will be written. The class of regular language, we can say regular sets over the summation, is going to give the following cases. The first, phi is a regular language, so it is an empty set of the regular language. Then whenever this condition will occur, that is going to give that is a set of A, small a, that is going to give the regular language, that is also a kind of set of that. Whenever the two sets will be occurred, L1 and L2, capital L1 and L2 from this regular languages, so there will be three operations will be occurred. The first operation is concatenation. In the concatenation, L1 dot L2 will be occur. That is going to give the concatenation of these two sets at one place. And whenever the two sets union is occur, L1 union L2, that is going to give the disjunction of L1 and L2 two sets. And whenever L1 and asterisk will be occur, that is going to give the lean closure out of L1 set, only from the L1 set. So this is how the different operation will occur for the regular language. Now let's define these all cases. So three operations are concatenation, disjunction or union, that is called as J, and third is lean closure. So example, whenever all the counters, whenever it will occur with the asterisk, whenever it will occur with the plus sign, whenever it is occur with the combination of n in M state, that is having actually special case. Whenever we need to do repetition of the different state at different cases. So then we will use the lean closure out of that. So we can use the lean plus a asterisk sign out of that. So in that case, whenever we are having the repetition cases. So all the anchors can be thought of individual special symbols. The square brackets, whenever it will be used, that will be a kind of disjunction. That whenever I will write square bracket A, B, so that means I have to, there are two states are there, either A or B, either A, either B also. So that is a distinction of between these two. So thus, suppose it is true that a regular expression can be turned into a expression whenever that is only going to make use of these three operations at one place. Then only it is called as a regular expression. Let's talk about lean closure. So this language actually consists of strings. Suppose with A and B. So that is going to be followed at least two A's. If I am writing A and B, suppose if I am writing A and A, suppose I am writing B and B. So whenever it is going to be repeated, I can just use this with the help of this asterisk sign, a plus sign, followed by an exclamation point. So that is how, right? So the set of operators that allows us to say things like that some lean asterisk function is there, number of A's will be followed. So are based on the asterisk, commonly called as a lean closure, lean star closure. So the lean star means 0 or more occurrences of the immediately previous character that has been followed in that particular we can say pattern, that is going to make a regular expression out of that. So this is again same example of SIP talking. So this is how SIP make a different sounds out of that. So if there is many occurrences of same we can say input state, we can just use this lean star closure or lean plus closure. So whenever I will write the slash A asterisk and slash, that means any string of 0 or more A's has been occurred here, right? This will match a small a, either it is going to be small with many A's at one place, right? It can be 5 times A, it can be 6 times A, like, but it will also match with off minor, since the string off minor has 0 A's. So it means either it will going to match with one single A also. So the regular expression for matching one or more A will be, I need to write, in that case, I need to write slash double A and asterisk and slash closed. That means it is going to follow a 0 or more A's, right? That is how we can just differentiate by writing this different expressions at different places. We can also write more complex patterns out of that whenever it will repeat again and again with the help of this lean star closure or plus closure. Whenever I will write this square bracket AB, that is has been closed and asterisk, and that is going to be followed with this. So that is going to give the 0 or more A's or more B's at one place. So not 0 or more, right? Square bracket will be occurring whenever it will occur. So that is going to just match with the AAA, AB, ABA, BB, 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 like that. So these are all going to be just differentiate with each other. Whenever we put with square brackets, we will put without bracket, and when we will put a small a small AA, like that. Sometimes it is going to annoy whenever I have to write the regular expression for digits. So whenever I'll write to need to write 0, suppose 0 at 2 place, again 1 at 2 place, that is not correct actually. That is not going to make us confused. In that case, I need to write it in the starter way. So that is how it is going to occur at least one time. So For that actually I will use lean plus closure. That means actually one or more occurrences of the immediately preceding character or regular expression has been just used, that occurred. So thus the expression, if I write slash square bracket 0 dash 9 and the square bracket close, and I will put a plus, and that I will again put as that slash, that is going to give the normal way to specify a sequence of digits as one place. Means from 0 to 9 the digits can occur in this particular pattern, particular matches. Thus there are two ways to specify this SIP in that case also. So likewise we have used that. So slash b a asterisk and exclamation mark and slash, and again that second case we will write b a plus exclamation sign and slash. So likewise that we can also specify same cases with the different uses of lean closures. Let's see the regular expression operations. So regular language has having the 4 operations actually: intersection, differences, complementation, and reversal of the different cases. So for that case actually it will be used by the summation asterisk mark. That is means that is having the infinite set of possible strings formed for that particular alphabet, that is going to describe by the summation mark. So whenever we are following two sets, that is L1 and L2, that is going to give the intersection, then we need to do the understand by the L1 that is going to be intersect by the L2, means that is congesting a set of string that is having either in the L1 either in the L2, both case that is occurring in the both L1 and L2. Difference that will be followed by L1 minus L2, means the L1 whatever set of string is having in the L1, that is not into the L2, that is only occurs in the L1 only. Whatever I am writing before starting from the operation, that will be followed. Complement, that means if I am writing summation asterisk minus L1, means that all set of possible strings are not there in the L1 set, right? So like that. Reversal, if I will write L1 and I will do write capital R up of that, that is going to give the complement reversal of that. So set of reversal of all the strings that is going to be occurred in L1 set, that will be followed by this one symbol. So that is how these 4 operations will be just carried out. Inductive step can be there. So for the inductive step, we saw the each of the primitive operation of a regular expression, that was concatenation, union, and closure. So that can be imitated by the an automata. So that will be followed. The first is concatenation. So we just having the 2 strings having the 2 FSAs that is next to each other by connecting all the final states of FSA1 to the final state of FSA2 by that transition. So that is going to give the concatenation out of that. In the next slides, we will see how it is going to make the graph out of that when the 2 FSAs we will follow it, and when we are going to do the concatenation out of that. Second is closure. So whenever we will apply the closure, we connect all the finite state of the FSA that back to the initial state, that is going to give the epsilon transition, that is going to implement the repetition part of lean closure, that asterisk closure, and then going to put the direct link between them from the initial state to final state by the this epsilon transition, that is going to implement the possible having the 0 occurrences at each point. Means we can say that we cannot leave out this part to implement lean plus closure instead of this closure state. Then I will just follow the in union. Whenever we will add the single new initial state, that is Q0, that is going to give the new transition from it to all the former initial state, that is going to give to the other 2 machines, that is going to be joined at one place. So again, nothing we have to do, we have to just combine 2 machines at each place, and that is going to be just completed with the initial state Q0 to new transition, and that is going to form again a finite state automata at one place. So in the next slide, I will show you how it is going to be just made So suppose we have seen the why how concatenation is going to be occur. So whenever we are having the two finite state FSA1 and FSA2, that is going to be depend on the different states, and that it is going to make how it is going to be just concatenate to each other. This is how we can represent. So the initial state from the FSA2 is going to be just depend on the FSA1. Likewise, that the lean closure of this FSA at one place, how it is going to be combined, that we can represent by this this graph of the finite state. So here the finite state will be starting from here, but it will depend with the different closures in between with the different initial states and different between states, and that is going to complete with the final state. So this I will talk about this all graph in the next upcoming we can say lectures, but only let's discuss about how it is going to be just combined at one place, how it is going to be union at one place, how we can just have the different form of lean closures, and how we are going to combine those in the form of regular language, either in the form of this finite state automated graph. Let's discuss about that union of these two FSA also. So if I have taken the FSA1, FSA2, how it is going to be combined. So it is for those two FSAs, it is going to make initial points, initial states, and that is going to be combined with the this transition states, transition function, that is epsilon, and then it is going to be depend on the all the different cases for the each finite state automata and their cases. This is how the finite state automata is going to be just carried out with the regular expressions and regular languages in our natural language processing language. So that is all about today's topic. Thank you for watching.
Like, share and subscribe. Hit the bell icon for more updates.